Hi, my name is Noah Arnold, and this is my Physics Lab 3. The purpose of this lab is to find the mass of a black hole by analyzing a star's orbit and then use this information to find the initial velocity that a ship must have when it leaves the surface of a planet so that it flies around the planet without crashing into either the black hole or the planet. We can do this using some fundamental physics principles. One of these principles is Newton's second law, the momentum principle, and then another fundamental physical principle that we use is the universal law of gravitation. The main physical principles that you will see used in the coding and the formulas that I will use are the formulas for universal gravitation, which can be seen here, and also the formulas from Newton's second law and the momentum principle, which can be seen here. You can also take, as well as the momentum principle being the change in momentum over the change in time, it could also be the net parallel and the net perpendicular forces added together. In this scenario, we are assuming that we are in space, so the only force acting on the spaceship that we're in and the star are the gravity of the black hole, and for the spaceship, the gravity from the planet as well. So that's what we are assuming in this case scenario. We're also assuming that after the initial velocity, the only things acting on the ship are again those forces of gravity. After plugging these formulas and our initial conditions into the coding program, we get that the final mass of the black hole is 7.29984 times 10 to the 33rd kilograms. For part 2 of this problem, we needed to find out how fast a spaceship needed to go at first in order to avoid hitting a black hole and a planet. After plugging in the value that we found for the mass of the black hole and the formulas that are needed for this problem, the universal gravitation, Newton's second law, and the position and velocity update formulas, I found that the initial velocity of the spacecraft was negative 5.26 times 10 to the 6th in the x component and 6.9 times 10 to the 6th in the y component, meters per second. After 60 minutes, the spacecraft is now 1.62 times 10 to the 10th miles away, meters away. Even though this experiment was completely done through the computer, there are some possible sources of error. I could have the incorrect velocity because I used the guess and check method, so there is a possibility that there is a smaller initial velocity that also would have avoided the black hole and the planet. The time interval could also be too short. The 60-minute time interval could have been longer, and that could have led to finding a different initial velocity in part 2. For the what if portion of the lab, we were asked, instead of wanting to escape the black hole, if we wanted to orbit around the black hole, what would be a velocity that we could have? In order to avoid the planet, we would have to have a larger y component and a smaller x component than the planet. And the velocity that I found for this ship that could do this is negative 2.9 times 10 to the 6th in the x component and 7.0 times 10 to the 6th in the y component. In the next part, we were asked how the net force and its parallel and perpendicular components are different than the rate of change of momentum and its parallel and perpendicular components, and the answer there is that they are the same, but that the change in momentum is easier to find than the net force.